Okay, can you hear me? Wonderful. I'll try to keep that time. Thank you everyone for being here and thank you for inviting me. What I'm going to talk about is kind of a follow-up to what we discussed in the panel session as well, and some more things as well. Let's see how I do on time. So the basic idea is to think about how do we bring ideas of automation and all of the excitement that is happening in robot learning to the space of lab automation. And I argue that to do that, you will need to think about both models, algorithms, and also frameworks and systems and data. Basically, you need a mechanism to solve the problem and you need data. And at least in this case, what happens is all of our friends in computer vision have a shit ton of data. We got inspired by all of the people doing LLMs. So we want to do robotics and foundation models. And we want to figure out what is the robot GPT. There's just one little problem. The problem is robotics is many things. It's warehouse, it's kitchen, it's lab, it's all those things. Can't have data sets for those things. And even more importantly, robot data just doesn't happen to be lying around on the web to be mined. You need to create it. It's very different from vision and language. And this is where simulation comes in, right? That you can really think about how to create data with the simulation that is efficient. And then this is exactly where it comes. That scale by itself is not sufficient. You really also need to think about algorithms. In this particular case, if we have the data pipeline, ideally we would like to solve these problems with a single model. I don't want to be solving one problem at a time. It has not been a scalable solution. Right. So what I'm going to talk about is two things, two ideas that we have found very exciting. One, thinking about how we can leverage language models for general purpose planning and control. And we'll give you one example of how we were able to bring that idea to lab automation. And then we'll also talk about what sort of frameworks and simulations do we actually need, and how can we help each other build a community like that. Okay, so one thing that has been very, very exciting is it might not even be news to you, is we want to talk to our robots and tell them what to do. The problem is the gap. When you tell ChatGPT, I want my robot to do X, ChatGPT needs to be able to talk to your robot, but your robot doesn't understand English. So this is where the community is sort of arguing that maybe thinking about talking to an LLM, but LLM outputting code, which is formerly known as program synthesis, is a very good idea. And then this is something that became super popular in about last year. There were like dozens of papers and we worked on it as well. And the basic idea goes like this. You tell the robot, I want to make coffee. The robot generates a high-level plan. You need to go to the kitchen, grab the cup, so on and so forth. Then it outputs something that is in English. Of course, English is not executable on the robot. So you have to figure out what we'll do. We'll create a plan that is code-like. Notice I use the word code-like. So this is not Python, this is Pythonic. It's readable, but at the same time, it's also machine readable. Now, the system basically uses this to output a code. The code, because it's code, you can pass it out directly to an interpreter. If it's successful and useful, you give it to your robot. If it's somehow incorrect, and there are many ways to be incorrect, you pass it back and then loop again, try again. Right? And this allows us to do very, very interesting things. We can build systems which can say, put the banana in the plate. Notice that there is, like, I'm not training it with the banana or the plate or anything. All of this is just zero shot. This is the kind of thing that I was saying earlier that we need in our lab. Put powder A in place B, right? You don't want to locate these things. You don't want to detect these things. This should be general purpose, right? We were able to extend this to chemistry-like experiments, grade chemistry-like experiments. It's like, make baking soda to cabbage solution. So you go from that to a structured language that is Kydeal-like, not necessarily Kydeal complete. You can make lemonade, of course. And you can have very specific instructions, right? Add 15 grams of this, and notice that there are these components from the chemistry lab that are now in the system. And you let the LLM know what exists in the system so that it can actually figure out how to use it. Okay? So this was the beginning of what we call Organa. Organa is the assistant that you wanted that does everything in the lab. And of course, this is a first prototype. I don't want to say that this is the solution, but this is what I believe will be the solution. What you really want is a system that you can talk to or interact with in a very no-code manner, ideally even very much like language. What happened last week, right? Google and OpenAI released their new models where you can just talk to the system, Astra and the GPT-4o. And they're basically like this. You can talk to the system. You want the system to be flexible. It is important that you want to be able to do many things. You have one kitchen, but many recipes. And then you want the system to be modular because the system should be able to improve as components improve. This is the big picture architecture, but I don't want to get into the details of it, but I want you to understand the big picture point. The big picture point is you talk to the system, there's an LLM that talks to you. The LLM calls a system that creates a plan, like what to do with what you want. Then that plan is passed on to a robot that executes that plan. The robot outputs something that is analyzed, and based on that analysis, you will do the experiment again, or you'll basically have the human come in the loop. Notice the human interacts with the system only at planning and analysis level. Right? The human is not doing all of the robot stuff. So I don't know if the volume will play here. But this is how it would work. There is a user. The user is the first author here in this case. And Marta talks to the robot. And we don't have captions, but basically she's saying something of the effect, Organa, I want to do X. And then Organa talks back. And she asks questions, or I should not be using she. Organa asks questions. And basically, in this dialogue, what is being established is the parameters of the experiment. This is what I want to do, and this is how you can do it. Right? Now, if we were to use simple LLMs to just output naively what needs to be done, there can be places where there are errors. LLMs hallucinate all the time. We do not expect them to be correct, especially in a domain which is not what they're trained on. So this is where we have a prior work which we called Clarify. Clarify basically allows you to fix LLM output to be meaningful and, let's say, robot viable. You might have a ideal output, but the robot, if the robot asks LLM to output KIDEAL, the output version or the formatting of the KIDEAL might not be correct. It may not work. It may be gibberish. So this is the framework where we basically say you interact with the LLM outputs KIDEAL, and the framework checks if the output language and the structure makes sense syntactically, in the sense this is correct language, makes sense semantically. You are basically saying move the beaker, but there is no beaker in the environment. Don't hallucinate stuff. So fix it. And then iteratively, this fix is done without a human in the loop, such that the output prediction is viable or acceptable. Furthermore, there is human in the loop which can tell the Organa what are the things in the environment. So I think Rafael said that I want to be able to add new things. This is that. You can basically say, there's a beaker, there's a weighing scale, there's a beaker here, the beaker contains X, and there's this other weighing scale. And now the human in the loop process basically can say, you can have human in the loop for doing history of experiments. You can ask the LLM, what do you see? If the observations don't make sense, you can provide feedback. So this is the setup phase, right? Phase 2 of this system is once the task has been specified, you go to task planning. In this case, we use the latest and the greatest in robot task planning. I don't want to bore you with the details of how this works, but it works. This is something that is the workhorse in robotics, PDDL-based task planning. This can, of course, be based on machine learning as well, but you can use different modular components. The system allows scheduling, so you can have more than one robots while planning. So you're not only doing larger tasks, but you can also make sure that they are multiplexed, so you can increase the utility of the system. And now it's that robot actually. So you might have perception modules and action modules. You will have the robot, of course, but you'll have other things. Other things meaning you might have devices and sensors and characterization devices. All sorts of them, they need to be interfaced. So the language model and the decision system needs to know what exists in the world so that you can use it. And then we have a perception system that is also based on foundation models that is zero shot. So you do not need to train it for your beakers or your lab. It should, in principle, work out of the box mostly. So this is what an experiment looks like. You told Organa to do an electrochemistry experiment. It figures out how to use the pump. This is running, of course, at high speed, and then it is moving things around. The important thing to note here is we did not structure this. This is slightly different from automation in the sense that it can do many things depending on what the input is, as long as the process parameters and the process, let's say, equipment exists in the environment. So if you ask it to use weighing scale, it can use weighing scale. Now, these are the places where you can parameterize things, meaning you might have different types of weighing scales. Some of the weighing scales might directly be digitally interfaced, so you don't need the robot to turn it on. Some of them might actually need a button to be pressed. All of that, in principle, is possible, but those things need to be built in. We need to do that. I do want to claim, even though I'm very excited about this, this is not a silver bullet yet, so don't get carried away yet. So we tried a bunch of experiments. So we tried solubility, recrystallization, pH measurements experiments. Each of these things have a few seconds, a few steps, like of the order of 5 to 10, and the mean time to execution is of the order of minutes. So you need long-term autonomy and memory so that the system doesn't sort of stop working, right? The interesting thing is, at the end of the experiment, it generates reports automatically. This is exactly what you want, right? You want graphs, you want plots, and you want effectively what the synthesized output is. And this is one iteration, because Organa in principle operates iteratively. Like you can have iteration 1, then you might say, okay, you did not do this right, or why don't you do this other thing? And it can go back and do this. In the panel session this morning, I was also talking about different levels of abstraction. So Organa essentially does the low level. Everything that is physical and moves is this, but all of the high level AI-based decision making and let's say potential synthesis or generation of possible things to do is still a high level model. And you can have different models simultaneously working together. This is an important thing to understand, that even though human is in the loop, human is not on standby all the time. So in an order of, let's say, an hour or so, the human is actually asked for about 1 minute in the loop. So a single human can actually take care of 50 of these things fairly well, right? So you can do experiments like advanced electrochemistry experiments where you're basically measuring pH versus voltage. In this particular case, we are interested in generating Pourbaix plots. And Organa results in a reasonable Pourbaix plot that is comparable to what a human result would look like in the sense of iterations and data quality. To a chemist, it doesn't matter, or it shouldn't matter, how the robot does it as long as it does it, right? So this is the point we are trying to make, that you can do meaningful, non-trivial experiments and the data quality is kind of the same, at least for simple experiments. Of course, these are very simple experiments. So one thing I want to convince you is, this is not necessarily the solution, but this is definitely the right path towards building general purpose solutions where we build these systems and they work broadly. So that was one part of the system. Now, as I said, even if we did it in our lab, the ideal success of this system would be when it works in your lab, and you can just download and run. Right now, we have to do a bunch of engineering for each of the low-level components to work, right? We need to make sure that the robot can actually turn on and off things, or it knows where everything is. And this is the part where I believe simulation comes in. I am a very big, let's say, proponent of simulation. So I've been building what is called Orbit. This is not only for chemistry, but actually generally all of robotics, building common frameworks that helps roboticists and all sorts of robot learning. We have built what is called ISAC Orbit. It's a general purpose thing. You can do all sorts of tasks with robots, whether it's folding t-shirts, pouring water cups, and it doesn't even have to be fixed robots. You can have all sorts of your robot. It could also be bring your own robot. A bunch of environments and assets are inbuilt. We provide with generic examples so that you know how to do development. It works with soft objects, t-shirts, cloth, fluids. And the interesting thing is, we are not being prescriptive of how you will solve your problem. If you are interested in machine learning, do that. If you're interested in motion planning, do that. So you can do this. You can test and evaluate. I think Rafael was saying that it's good to test that a robot, when moving, will not hit the limits of something. You can test the existence of a human in the environment. You can put it on real robot, if that's what you like. And even more importantly, particularly for laboratory automation people, you can do remote teleop. And that means you can do remote monitoring. If something doesn't work or robot is not able to do it, it can call you. And all you need to do is Zoom call into the system. So all you need is a phone, and you can remotely teleop the robot to do whatever it needs. So for example, there's something that robot is stuck on, you can help it. You don't need to be in the lab. So remote telemetry is very useful. The cool thing is, all of this is open source. You can use it now. It is fairly general purpose. And it has an active community of developers. So if you find something that doesn't exist, please contribute back. To convince you that this is fairly general purpose, NVIDIA has adopted this for its current effort in humanoids, and it's throwing a lot of heft behind this. We were able to generalize this idea, because this is general purpose, to surgery. This was a paper that was presented yesterday. You can build, you can bring a surgical robot in and do fancy stuff like threads and rubber sutures. We have already interfaced LLMs with it. So you can talk to it. So a surgeon can say, pick up the needle and do this, and then do that, and this thing works. And importantly, a collaboration with organizers. We are building what I would like to say is, is Autolab, where we are now bringing chemistry-relevant objects, tasks, assets, materials in the system. It's not there yet, but we need all of you to help us out. We want this to be a community effort. We do not necessarily need to own it. Only when done together would this be useful. And the vision I have here is, for all of us, we converge on some platform that we can use together to create benchmarks and make progress on this together. With that, I would like to thank you all. Happy to take questions, and I'm very glad that I have the privilege of your time.
Thank you so much. Let's thank our speaker. Thank you.
Happy to take questions. Yes. Yes, please. Oh, it's a multimodal system. You can already type things in, if that's what you want. So both of those interfaces already exist. So if you believe speech is ambiguous or tedious, you can type it in. Yeah. So you can provide direct ideal if that's what you want. So you can go as detailed as necessary. Yeah. As long as it's text, it's all the same. Yeah.
Okay, let's thanks again our speaker, and